Hello everyone. In this lesson we will be exploring Ampere's law, a foundational concept in electromagnetism. Ampere's law is crucial for understanding how electric currents produce magnetic fields, and it is one of Maxwell's four equations that describe the behavior of electric and magnetic fields in space. We will talk about Maxwell's equations soon. In the meantime, Ampere's law, named after French physicist André-Marie Ampère, describes the relationship between the magnetic field in space and the electric current that produces it. This law states that the magnetic field around a closed loop is proportional to the electric current passing through that loop. Mathematically, we express Ampere's law as follows. The closed integral of the magnetic field along a path is equal to mu naught times the current enclosed, where B is the magnetic field vector, dl represents an infinitesimal vector element of a closed path, mu naught is the permeability of free space, it is a constant with a value of approximately 4 pi times 10 to the negative 7 newtons over ampere square, and I enclosed is the enclosed current, or the total current passing through the area surrounded by the closed loop. Ampere's law tells us that the line integral of the magnetic field along the closed path is proportional to the total current passing through that path. To fully understand Ampere's law, let's think about the physical implications of this equation. This law essentially says that a current flowing through a conductor generates a magnetic field that circles around the conductor. The direction of the magnetic field follows the right-hand rule. If you point your thumb of your right hand in the direction of the current, your fingers will curl in the direction of the magnetic field. You can visualize this integral the following way. Imagine that you are in the laboratory with a long wire that carries a current. If you make an imaginary loop around it and you measure the magnetic field along this path and you make lots of measurements as you move slowly along this path, you add the values together, multiply by the distance between measurements, and then what you've got is the actual integral. Remember that an integral is the sum taken to the limit of small distances dl. This law is especially useful when we are dealing with situations that have symmetry, such as an infinitely long straight conductor or a solenoid. In these cases, Ampere's law allows us to simplify our calculations significantly. These situations allow us to select a convenient path known as an Amperean loop, where the magnetic field is either constant or zero. For instance, around an infinitely long straight wire carrying current I, we choose a circular path concentric with the wire. At a given distance from the wire, due to the symmetry, the magnitude of the B field has to be the same. There should not be a preferred direction. This symmetry allows us to say that the magnetic field magnitude B is the same at all points along the loop. And take that out of the integral. Applying Ampere's law, here we have that the closed integral along the path of B dot dl is B 2 pi r, and that's equal to mu naught I. Solving for B, we find that B, the magnetic field, is just mu naught I over 2 pi r. This result tells us that the magnetic field around a straight, infinitely long current-carrying conductor decreases with the distance r from the conductor. Let's now examine a hollow cylindrical conductor with an outer radius r and a current I flowing uniformly distributed along its walls. We are interested in determining the magnetic field at different radial distances from the center of this conductor. To understand this problem, let's break it down into regions. Inside the hollow part of the conductor, the distances are smaller than capital R, and outside the conductor, where the distances are greater than capital R. In region 1, inside the hollow path of the conductor, there is no current enclosed by an Amperean loop with radius r smaller than capital R. by Ampere's law, the enclosed current is zero because all the current flows along the outer wall. Therefore, the magnetic field in this region is zero. So the closed integral of B dot dl, which is equal to mu naught I, is equal to zero because there is no I. So for r is smaller than r, B is equal to zero. In region 2, for a point outside the hollow conductor where r is greater than capital R, let's assume a circular imperial loop of radius r, which now encloses the entire current I, where we can apply Ampere's law directly. The closed integral of B dot dl, which is B times 2 pi r, which is mu naught times I. So solving for B, we find again that B is mu naught I over 2 pi r. So for r greater than capital R, B decreases with the distance r, as B equals to mu naught I over 2 pi r. Ampere's law is also essential in the design of devices such as electromagnets, transformers, and inductors. We can and will apply Ampere's law to calculate magnetic fields in these devices and optimize them for energy efficiency and performance. Ampere's law is also relevant in magnetic levitation systems, such as in medical devices, as MRI machines, where magnetic fields must be controlled and predicted precisely. Ampere's law provides a fundamental link between electric currents and the magnetic fields they produce. The law is essentially useful in scenarios with symmetry, allowing us to calculate fields efficiently. Let me know your questions in the comments below, and may science be with you.